All right, so in this video, we're going to introduce vector fields in R3. So similar to what we saw in R2, the input for the vector field will be a point, in this case, a point in three-dimensional space. And the output is going to be a three-dimensional vector with an I, a j, and now a k component. And these functions p, q, and r we'll refer to as the component functions of the vector field f. And we'll adopt that same convention that says that the output vector will have its tail located at your input point, here x, y, z. Okay, so to get a feel for some vectors in R3, let's look at question 4 on the worksheet that says to match each vector field in A through D with its corresponding plot in 1 through 4. So part A, we have the f is I plus 2j plus 3k. Well, this is a constant vector. So that says that no matter where you are in three-dimensional space, the output vector will always be the same. And I see that is the case in plot 4. So A is paired with 4. Now, for B, we have that f is I plus 2j plus zk. So I and j are constant, but k here now varies with z. And so if we're, say, above the xy plane where z is positive, all the vectors are going to have a k component that's positive, so they're all going to be pointing upwards. If I'm below the xy plane where z is negative, then the k component's negative, so I'm going to have a bunch of vectors pointing downwards. And I see that's the case in plot 1. So B is paired with 1. All right, for C, f is xi plus yj plus 3k. I have a constant k component, right, 3k. So that says all my vectors are going to be pointing upwards with a k component of 3. So that's going to be, or I can see that here in plot 3. And then lastly, for D, the field is f is xi plus yj plus zk. Notice that this is the position vector of the point x, y, z. So if I'm at, say, this location whose coordinates are x, y, z, just think about drawing the position vector from the origin to that location, and then just translate that vector so its tail is at that location, right? We can see that all of these vectors point radially outward from the origin. Okay, so this is the three-dimensional analog of the radial field that we introduced in problem 1, right, in R2. Okay, so D and 2 are paired. All right, so last thing I'll say in this video is that, as you can see with these plots, drawing a vector field in R3 by hand is just not feasible. Okay, so using some technology is definitely the way to go. And math3d.org does plot vector fields in R3 quite nicely. So here's an example, xi plus yj plus just k. So if I'm looking down, so this is the xy plane, the xi plus yj portion, right, that's just the radial field from problem 1. And then since the k component here is just constant 1, that says all of these vectors are going to be pointing upwards with a k component equal to 1. And I can see that pretty clearly as I scan through. Okay, so I recommend just playing around with this and looking at some other fields just to get kind of a feel for how these things behave. But again, yeah, technology is certainly the way to go if you are given a general field, especially if the component functions are complicated. All right, we'll stop there. Thanks.